Welcome everybody. In this video segment, we will be taking a look at section 7.8 in our textbook. In section 7.8, we're not looking at any new techniques of integration. We have all the techniques we need for us for the rest of the course. But we're going to look at a special kind of definite integral. The title of this section is Improper Integrals. So we're looking at section 7.8. And the title is Improper Integrals. Improper Integrals. So rather than diving right into the definition first, I think we'll develop an idea of what an improper integral is by looking at a simple but multi-part example. So this example, except for the last part, this example is going to be nothing more than something we might see in a Calculus 1 setting. So, for example, I want to find the area bounded between a curve y equals 1 over x squared and the x-axis between two limits. So let me write that down for us. So the problem is to find the area bounded by the curve y equals 1 over x squared and the x-axis so the x-axis is below x-axis, oops, okay, this will work. So find the area bounded by y equals 1 over x squared and the x-axis from x equals 1 to, and this is where we're going to start building this as a multi-part problem, to part A, x equals 2. Okay, so it's a very simple problem from Calc 1. So let's review how we would solve this problem. In order to solve this problem, it's a good idea to, or any area problem, it's a good idea to, if possible, get the graph of the region we're finding the area of. So let's take a look at the graph of this function. So the graph of y equals 1 over x squared looks about like that. It's nothing more than a function that we looked at a whole bunch of times since pre-calculus, and I want the area from x equals 1 to x equals 2. Okay, so remember that we want the area bounded between the x-axis and a non-negative function, that is a function that lies above the x-axis. What we do is we integrate the function between the two limits of integration, x equals 1 and 2 in this case. So the area is nothing more than the definite integral from 1 to 2 of 1 over x squared dx. So let's just use the fundamental theorem of calculus to evaluate this integral. The integral of 1 over x squared is, or antiderivative of 1 over x squared is negative 1 over x. And this is carried between 1 and 2. And if we substitute the upper limit of integration, we get negative 1/2. If we substitute the lower limit of integration and subtract, we get plus 1. So the area is 1/2 of a square unit. Okay, nothing real exciting, nothing real difficult. This is something we would do frequently. This is in Calculus 1. This is a really kind of a low-level Calc 1 problem. For the next example, I want to find the area underneath this curve again and above the x-axis, but instead of going from 1 to 2, I want to find the area between x equals 1 and x equals 10. Okay, so let's do that now. So B, I want to find the area between x equals 1 and x equals 10. So let's take a look at what happens graphically. So once again, we'll look at the graph of the function. I'm going to extend it a little bit because the right hand limit of integration is a bit farther than x equals 2. Function is still 1 over x squared which approaches asymptotically the x-axis, so x equals 1, to say x equals 10. All right. Again, this is a simple Calc 1 problem. The area equals then the integral from x equals 1 to 10 of 1 over x dx. The antiderivative doesn't change because we changed our limits of integration, 1 over x squared, excuse me. The antiderivative is negative 1 over x from 1 to 10. And this becomes negative 1/10 plus 1, or 9/10 of a square unit. So the area bounded by the curve y equals 1 over x squared, and the x-axis between x equals 1 and 10 is 9/10. For our third example, you can kind of guess where I might be going from here. In the third part of this example, I want to increase the right-hand limit of integration again, but by a lot more. I want to go from x equals 1 to x equals 100. Okay, once again, we consider the graph of our function. It's the same function, 1 over x squared, looks like this, asymptotically approaches the x-axis. This isn't going to be quite to scale, so here's x equals 1. Let's assume that way out here is x equals 100. From the previous part of the example, x equals 10. Again, this is not going to be to scale. X equals 10 would have been about right here. Okay, so the previous example, we found this area. This area was 9/10. So what do we expect for the area to be now? In fact, we can probably guess what's going on here. If I integrated between 1 and 2, the area was a half a square unit. If I increase the right-hand limit to 10, the area was 1/10, or 9/10 rather. So I can expect maybe, or not maybe, that the area then will be more than 9/10. So the big question is the area going to become bigger as I increase the right-hand limit of integration? Is it going to approach some sort of constant as I keep increasing the right-hand limit of integration? Well, let's not get too far ahead of ourselves here. The area is then the integral between 1 and 100 of 1 over x squared. Antiderivative doesn't change. It's negative 1 over x. Let me clean that up just a little bit. So negative 1, oops, didn't clean it up that much, between 1 and 100. I want to get rid of this stray mark here. It looks like a negative. Okay, so the area is negative 1 over 100 plus 1, or 99 over 100. So now we're getting a really good idea of what's happening as we keep increasing the right-hand limit of integration. As we let x get larger and larger and larger, it looks like the area of these corresponding regions are approaching 1. We got an area of 1/2 between 1 and 2, of 9/10 between 1 and 10, and 99 over 100 between 1 and 100. If we were to integrate between 1 and 1,000, we would get 999 over 1,000. So these areas are approaching a definite number as the right-hand limit of integration keeps getting bigger and bigger. And that's basically what we're going to do to define or this thing we call an improper integral. I want to take kind of a big leap now. For part D, I want to find the area between x equals 1 and x equals infinity. Now, since it doesn't really make sense to have an upper limit that's not a number, at least for the time being, we can interpret this as I want to find the area between the curve y equals 1 over x squared and the x-axis to the right of x equals 1. Okay. Okay, but in doing that, though, we're going to set up an integral just like we would do in Calc 1 to a point. The area then is the integral from 1, and we're going to allow ourselves to put in the symbol infinity here for the upper limit of integration, even though infinity is not a number. And the integral is of 1 over x squared with respect to x. And the way we're going to handle this problem where the upper limit is not a number is we're going to replace the upper limit with a value, a distinct value, and not infinity. So here's our curve again. Y equals 1 over x squared. What we're going to do is we're going to integrate between 1 and some distinct right-hand limit of right-hand endpoint. So integrate from 1 to t. That'll give us a very specific amount of area. And in the end, we'll take the limit of that area as t approaches infinity. Let me put all that together. I kind of threw out a lot of information there. We're going to integrate between 1 and t, where t is unspecified, just some number more than 1. 1 over x squared dx. And then in the end, we're going to take the limit as t approaches infinity of that value, and we're going to define that as the area to the right of x equals 1, or in practical terms, from the area bounded between the x-axis and 1 over x squared between x equals 1 and 100, and infinity, not 100, sorry. Okay, so let's evaluate this limit. So this is going to equal the limit as t approaches infinity. Let's evaluate the integral within this limit. The antiderivative, or an antiderivative of 1 over x squared is negative 1 over x from 1 to t. So this is equal to the limit as t approaches infinity of substituting the upper limit of integration, negative 1 over t, subtracting the value of the antiderivative at the lower limit, plus 1, and then we'll take the limit as t approaches infinity. We found the integral from 1 to t. It's some finite amount. It's this negative 1 over t plus 1. As t approaches infinity, 1 over t approaches 0. So we get exactly what we might have expected. We get 1 square unit of area as t approaches infinity. No big surprise, because the numbers were increasing as the upper limit of integration increased. If the upper limit of integration was 2, we got an area of 1/2. When the upper limit of integration was pushed out to 10, we got an area of 9/10. See if I can do this. It's not going to let me do this. It's not going to let me color this red. All right, well then I'll accept that we're not going to cover. I'm going to try one more time. All right, I guess it's not going to let me do it. And when we increase the right-hand limit of integration to x equals 100, let's see if it'll let me do. Oops. We got an integral. No, it's not letting me do it. All right, sorry about that glitch, folks. We got an area of 99 over 100. So as we keep increasing x, we expect our limit to be 1. We are getting closer and closer and closer to 1. This, the bottom line of all this is, what this is bringing up is the concept of an improper integral. Now it writes in red. Proper integral. In this section, we talk about two types of improper integrals. We're going to call this a type 1 improper integral. So this, what we just talked about in part D of this example, was an example of what's called a type 1 improper integral. This integral looked like, for us, it was the integral from 1 to infinity of 1 over x squared with respect to x. And what makes it an improper integral is when one or both of the limits of integration are infinite. Okay, so let's take a look at another case. Let's take a look at the integral from, let's say, oops, and I can't stop it from writing in red. Let's take a look at the integral from, let's say, 1. Let me clean that up a little. The integral from 1 to infinity of 1 over x dx. Okay, so what we do is we integrate between 1 and some constant t of the function 1 over x with respect to x. Then we take the limit of this quantity as the upper limit of integration becomes infinite. And again, the interpretation of this graphically is pretty much the same. Y equals 1 over x looks about like that. We're interested in essentially the area to the right of x equals 1. So if here's x equals 1, I want the area underneath the curve to the right of x equals 1. To do this, I integrate between 1 and some constant. That's the only restriction on the constant is somewhere more than 1. Then I drag that constant to infinity to get the entire area. Or in this case, just since we're just not really considering an area problem, the value of this integral. All right, so let's do this. This is the limit as t approaches infinity. The antiderivative of 1 over x is the natural log of the absolute value of x. This is carried between 1 and t. So this is the limit as t approaches infinity of the natural log of t. No absolute value is necessary. I'm assuming that t is some positive number more than 1, minus the natural logarithm of 1. So this becomes the limit as t approaches infinity of the natural log of t. Now the natural log of t, as t approaches infinity, it approaches infinity very slowly. Remember, the natural log function grows extremely slowly, but eventually this integral approaches infinity. Okay, so this curve doesn't capture a finite amount of area between 1 and infinity. Okay, so let's take a look at what we have so far. We've looked at 2 improper integrals so far. We've looked at the integral from 1 to infinity of 1 over x squared dx, and we determined the value of this improper integral was 1. So now let's look at some terminology that's associated with improper integrals. Since this first integral was equal to 1, we say that the improper integral converges. Okay, we say that this improper integral converges. Oops. This concept of convergence is the central concept that will take us to the end of our course. We're going to be considering convergence and one more thing related to it throughout the semester. So this improper integral is said to converge, or this improper integral converges. In fact, the improper integral converges to 1. Okay, in the second improper integral, the integral from 1 to infinity of 1 over x with respect to x, this improper integral did not converge to a constant. This improper integral was infinite. So we say, no big surprise, that this improper integral diverges. This improper integral is divergent, or diverges. So the concept of convergence is it's the central topic for, I think I mentioned that, for the rest of our semester. And for improper integrals will do one of two things. They will either converge or diverge. If the improper integral equals a constant, that is, if this integral is a limit equals a constant, the integral converges. If it doesn't equal a constant, then it diverges. One quick note before we move on is that divergence doesn't mean that the integral approaches infinity. Divergence simply means that the integral doesn't converge. Okay, so if an improper integral doesn't equal a constant, it diverges. Very often we get a divergence corresponding to an improper integral equaling infinity, but it's not necessarily the case. Okay, let's take a look at the possible general cases for a type 1 improper integral, and then we'll look at some more examples. So suppose we want to define this thing called an improper integral of type 1. So a type 1 improper integral, type M1 improper integral occurs when one of three different cases, in one of three different cases. So let's say case I. Case I is where the upper limit of integration is infinite. If the upper limit of integration is infinite, you approach this case by doing exactly the same thing we just did with the last two cases. Be a good idea if you had a graph of the function, but it's not always necessary. So we're integrating between a and infinity. To integrate between a and infinity, we integrate between a and t. And then we take the limit of this quantity as t approaches infinity. So that's how we handle the first of the three cases that occur with type 1 improper integrals. So the second case, you can probably guess where this is coming from. Let's say case II. We're looking at the possibility that the lower limit of integration is infinite. So we have the integral from, let's say, negative infinity to b of the function f of x with respect to x. In this case, again, let's get a quick graph of this situation. In this case, we have a function and we're integrating, oops, I need to change things up a little bit. I was going to draw the same thing, but our function isn't, the lower limit of integration is from negative infinity. So let's do this. So if we're looking at the lower limit of integration is negative infinity, it corresponds to something like this. I'm interested in the area, if we interpret this as an area problem, to the left of b. So the way we handle that is to integrate, instead of all the way to negative infinity to begin with, we integrate from t to some b, and then let t approach negative infinity. So this second case would look like the limit as t approaches negative infinity of the integral from t to b of the function. So again, we evaluate the integral from t, the left-hand endpoint, t, some t that's some number less than b, to b, and then we evaluate that integral and finally let the lower limit of integration approach negative infinity. The only other case that happens in a type 1 improper integral is when both limits of integration are infinite. So if we're looking at the integral from negative infinity to positive infinity of f of x with respect to x. The way we handle this, case case triple I, is to turn it into two integrals, one of case I and one of case double I. The way we handle this is to break up the integral into the integral from negative infinity to any constant, very often the constant is 0, of the function, plus the integral from that same constant to infinity of f of x dx, and then evaluate these two integrals. One is of type double I, and one is of type single I. And there we go again. Okay, this time I eliminate it. Okay, if either of these integrals diverges, then the entire integral, the original integral, is said to diverge. If both of the integrals converge, we add up their values, and then the original integral is said to converge to that number. So the bottom line is, there are really only two big cases to worry about. The upper limit's infinity or the lower limit's infinity. If both limits are infinity, break up the integral into two integrals and evaluate each of those integrals separately, or determine whether they converge or diverge separately. Okay, so let's take a look at another example. So let's see here. So, let's evaluate the integral. So let's say evaluate the integral from 1 to infinity again of 1 over 1 plus x squared with respect to x. Okay, so this is clearly a type I, type 1 integral, so 1I, since the upper limit of integration is infinite. So what we do is we integrate from 1 to some t, then we take the limit of that integral as t approaches infinity, 1 over 1 plus x squared. And we proceed with this. The very last thing we're going to do is evaluate the limit, so we just keep the limit symbol floating along until we find this antiderivative, or this definite integral. The integral of 1 over 1 plus x squared, what is it? You remember? No? Inverse tangent of x. One of our standard integrals from a month or so ago. So continuing on, we get the limit as t approaches infinity. The upper limit of integration is t, minus the lower limit of integration is 1. The inverse tangent of 1 is pi over 4. Remember, the tangent of pi over 4 is 1, so the inverse tangent of 1 is pi over 4. Finally, we take this limit. As t approaches infinity, remember the inverse tangent function has a horizontal asymptote. The inverse tangent function has a horizontal asymptote of pi over 2. So this is what the inverse tangent function looks like, at least to the right of the y-axis. Let's say the inverse tangent of t, y. So the value of this improper integral is pi over 2. Horizontal asymptote is pi over 2 minus pi over 4. So the value of this improper integral is pi over 4. We don't say square units because we're not interpreting this original integral as area. We could, but it wasn't an area problem. This integral converges to pi over 4. The integral converges to pi over 4. Okay, so let's take a look at, and I'm going to put it this way, and this is how I generally describe this integral. Let's look at the most important integral for us for the rest of the semester. This integral is going to come back again and again and again when we talk about series. a little bit of background. We determined that the integral from 1 to infinity of 1 over x squared dx converges. It converged to 1. We also determined that the integral of 1 over x to the first from 1 to infinity diverges. These two integrals are very special types of integrals. They're both reciprocal powers of x. The most important integral is, for our whole course, really, is the integral from 1 to infinity of 1 over x to some unspecified power. I'd like to know the values of this exponent p for which this integral converges. We know that if p equals 1, the integral diverges. The integral diverges. When p equals 1, we're integrating 1 over x. If p equals 2, the integral converges. Integral converges. So it seems like for some number, maybe between 1 and 2 for the exponent, there's a cutoff point. It seems like where the integral diverges for that value less than that, for p less than that, and converges otherwise. So let's handle this special integral for any possible value of p. So let's do that. Our next example is going to be to determine the values of p for which the integral I'm going to move this integral if my smart pen will allow me to. Boom. It did. For the integral that converges. Okay. Again, this integral, the integral of 1 over x to the p for x between 1 and infinity is singly the most important integral for our semester. The actual reasons for that we're going to have to hold off on for quite a bit of time, but keep have a little faith in me that this integral is gonna pop up often. In fact, this integral is so important we give it a special name. Let's call it a p integral. Very, very important integral. So let's figure out when this integral converges, when this integral diverges. Some values of p it converges, for some values of p it diverges. I'm going to break this down into two cases, and I think it'll be pretty clear in a second why I'm dividing it off into these two cases. So I'm going to say case 1. P equals 1. Okay. The second case is going to be case 2. P is not equal to 1. So let's say case 1. P equals 1. If p equals 1, we're looking at the integral of 1 over x to the first dx from 1 to infinity, and this integral diverges. We showed it about 10-15 minutes ago. Okay, so that takes care of one of the two cases to solve this problem. Case 2 is going to take us quite a bit more. Case 2, let's assume that p, the exponent in that integral, is not equal to 1. Okay, so let's go for it. So let's actually determine the solution to this by trying to evaluate the integral of 1 over x to the p dx from 1 to infinity. Okay, this is a type 1 small I case. So that is the upper limit is infinity. So to handle this, we take the limit of the integral from 1 to t, and then we let t approach infinity. I'm going to rewrite this function 1 over x to the p as x to the negative p with respect to x. So let's evaluate this integral. This is the limit as t approaches infinity. Now here's where it's going to become clear why I'm looking at the case where p is not equal to 1. If p were equal to 1, we'd be integrating 1 over x. And the integral of 1 over x is a logarithm. If p is not 1, we're just integrating a power, like from calculus 1. And when we integrate powers in calculus 1 and the power is not negative 1, or rather 1 over x to the 1, all we do is we use the power rule for antiderivatives. So the integral of negative x to the p then will be at negative x to the negative p plus 1 over negative p plus 1, carry between 1 and t, and then we take the limit as t approaches infinity. So this is the limit as t approaches infinity. Let's perform this integration. This is t to the negative p plus 1 over negative p plus 1, substituting x as t, minus 1 to the negative p plus 1 over negative p plus 1. And then we take the limit as t approaches infinity. This limit looks very complicated at first glance, but there's nothing really complicated going on here. The variable or the number t is not changing here. It's constant in this limit. And notice that it occurs in the denominator of both terms in this limit. So I'm going to factor that out. I'm going to factor out 1 over negative p plus 1. This then becomes times the limit as t approaches infinity of t to the negative p plus 1. And in the second term, this 1 to the negative p plus 1 has a very simple value. 1 to any power is 1. So the value of 1 to the negative p plus 1 is just 1. Okay, so that limit's a little easier to look at. Now here's where we get to our answer. We're looking at the limit as t approaches infinity of some power of t. If that exponent, if that negative p plus 1, if that exponent, negative p plus 1, is positive, then this limit's going to be infinity. If that exponent were 2, let's say if negative p plus 1 equals 2, you're looking at the limit of t squared minus 1. T squared goes to infinity. If negative p plus 1, that exponent were 3, t cubed minus 1 goes to infinity. If that negative p plus 1 is 1/2, t to the 1/2 minus 1 approaches infinity. The only way we're going to get this limit to exist, the only way we're going to get this limit to converge, is for that exponent to be negative. If the exponent is negative, that pops the variable into the denominator, and the limit then of that portion of the integral will be 0. If that's not clear, oops, I'm going to change back to black here. If that's not clear, then I'm going to rewrite this in a way that might make it more clear. I'm going to rewrite this term, t to the negative p plus 1, as 1 over t to the p minus 1. Okay, all I did is I took the negative of the exponent and I popped the power into the denominator using rules for exponents. As long as that exponent is positive, the limit of the first term will be 0, 1 over t to a positive number 0. If that exponent is negative, it brings the t back up into the numerator. The limit goes to infinity. So the limit just of the 1 over t to the p minus 1 as t approaches infinity, just the limit of that first term is going to equal one of two things. It's going to equal 0 if p minus 1 is positive, if that exponent is positive, and it's infinite, that limit doesn't exist, if the exponent p minus 1 is negative. Again, if the exponent is negative, it brings t into the numerator, t goes to infinity, limit goes to infinity. So if p minus 1 is greater than 0, that means that p is greater than 1. If p minus 1 is less than 0, that implies that p is less than 1. So we get our conclusion here. The value of the integral will be -1. Oops, let's redo that. The value of the integral will be 1 over negative p plus 1 times 0 minus 1 if p is greater than 1. Remember, if p is greater than 1, the limit of 1 over t to the p minus 1 will equal 0, and we'll get this integral converging then to -1 over negative p plus 1, or 1 over p minus 1, if p is greater than 1. If p is less than 1, that limit portion of the integral will diverge. If p is less than 1, the 1 over t to the p minus 1 approaches infinity. And that tells us then the integral will diverge. So, summarize. We already determined in the very brief case p equals 1 that the integral diverges. So if p equals 1, the integral diverges. So the bottom line is this integral we call the p integral, p as in Paul integral, does one of two things. This integral converges. In fact, it converges to 1 over p minus 1 if p is greater than 1, and diverges if p is less than 1. Case 1 also adds less than or equal to 1. What you want to do with this integral is memorize it. This integral is going to be, I think this is like the third or fourth time I've mentioned this, central in the rest of our course. The integral of 1 over x to the p converges to 1 over p minus 1 if p is greater than 1, and diverges if p is less than or equal to 1. The most important aspect of this integral is not the value, the value to which this integral might converge. The important idea with this integral is that the integral converges if p is greater than 1 and diverges otherwise if p is less than or equal to 1. The value of the convergent integral is not so much important in our later work. So what does this allow us to do, at least in this section, without going into our future? It tells us that immediately, if I want to consider the integral 1 over the square root of x, I don't have to go through the process of converting this integral to a limit. This is a p integral. This is the integral from 1 to infinity, 1 over x to the 1/2. This is a p integral with p equals 1/2. 1/2 is less than or equal to 1. So the integral diverges. If we were looking at the integral of from 1 to infinity of, let's say, x to the minus pi dx. I don't have to evaluate this integral by converting it to a limit and using the fundamental theorem, etc. This is nothing more than the integral of 1 over x to the pi dx. This is a p integral with p equals pi, and pi is more than 1. Oops. Turn that into an arrow here. So the integral converges. Okay. So to finish up this section, I want to talk about our type 2 improper integral. If you'd like, this would be an appropriate time. This would be a good place for you to take a break. And that's exactly what I'm going to do right this moment. All right, everybody, let's now consider our second type of improper integral. We'll call a type 2 improper integral. And just as we did with the first type, let's approach this concept with an example. And my example is going to be another seemingly similar example, or seemingly the same kind of an example we looked at Calc 1, but there's a difference hidden inside the actual problem. So let's get started. I want to find the area again. So I want to find the area bounded by and y equals 1 over the square root of x, and the x-axis between x equals 0 and x equals 1. So first of all, it's pretty clear this is not a type 1 improper integral. Neither of the limits of integration are infinite. If we were to continue as if this were a calculus 1 problem, we would say the area should be the integral from 0 to 1 of 1 over the square root of x dx. This is a problem. There's a problem here in the very setting up of this integral is the area. We can't do it. To see why this is the case, let's take a look at the graph of the function. Function is another really common pre-calc type of graph. Looks sort of like the graph of 1 over x or 1 over x squared. This is the graph of y equals 1 over the square root of x. Since its domain is only positive real numbers, we only get a graph in the first quadrant. And if we're interpreting this integral geometrically, or this area geometrically, what we're asked to do is find the area between 0 and 1, but the function becomes infinite as we approach the origin. So this area, or this region, extends infinitely vertically upward. So this is very different from what we encountered in Calculus 1. In Calculus 1, we never integrated or found area in a region where the function became infinite at a particular point. So that's essentially what makes the type 2 improper integral, is where we have a function that is not continuous within the interval of integration. Clearly, the function here is not continuous at x equals 0. So the way we handle this is kind of in a similar fashion to how we handled the type 1 integral. So let's take a look at, once again, the graph of this region. We're looking at the region from 0 to 1. And since we can't integrate at a point where the function becomes infinite, instead of integrating starting at 0, we push to the right ever so slightly. And by ever so slightly, just to a point that's, say, somewhere between 0 and 1, and we integrate from that point to 1. So we integrate from t to 1, which is perfectly legitimate. Within the interval from t to 1, the function stays finite. It's a little corny the way I've graphed, but there's no point at which the function becomes infinite if we put the lower limit as some positive constant t. So what we do is we say, okay, the area we're looking for is not quite the integral from t to 1 of 1 over the square root of x. But if after we find that integral, we then let t slide back to 0, then we can see that we'll be picking up all of the area in question. Now, the only additional detail here is that t can't approach 0 through both directions. T has to approach 0 through positive numbers. So literally what we did is we pushed the left limit forward to the right a little bit, and then we take the limit of the area formed with those new limits of integration and let t approach 0 back from the right. So let's evaluate this limit, and if it exists. So this is the limit as t approaches 0 from the right hand side. The only way t can approach 0 is from the right hand side of, well, let's evaluate this integral. This is the integral from t to 1 of x to the minus 1/2 dx. It's one of the simplest integrals from Calc 1, or antiderivatives from Calc 1. The antiderivative of x to the negative 1/2 is x to the negative 1/2 plus 1, which is x to the positive 1/2, over that same new exponent, positive 1/2. Well, if we invert and multiply, we'll get 2. So, and that is taken between t and 1. So using radical notation, this is the limit as t approaches 0 from the right of 2 times this, say, the square root of x from t to 1, or the limit as t approaches 0 from the right of 2 times the square root of 1 minus 2 times the square root of t. The square root of 1 is 1, so this is the limit as t approaches 0 from the right of 2 minus 2 times the square root of t. So, to evaluate this limit, finally, as t approaches 0 through positive numbers, the square root gets small, so the square root approaches 0, and we have an area of 2 square units. So this, again, this is an example of a type 2 improper integral. Let's generalize this. Let's look at the most general type 2 improper integral and the different kind of cases that might arise. So, type 2 improper integrals. Proper integrals. Let's say we're integrating between a and b of f of x dx. And a type 2 improper integral is where the function is discontinuous within the interval from a to b. F of x is discontinuous on the interval. Oops, this should spell continuous, right? Discontinuous on the interval from a to b. And just as with type 1 improper integrals, this breaks down into 3 subcases. So let's break down these subcases as subcases A, B, and C. And the first subcase we'll call a discontinuity. A discontinuity at x equals b. So what that means graphically is this. we have some function. The function is defined between is considered between a and b, but the function has some sort of discontinuity at the right-hand endpoint of our interval of integration. Although the function need not approach infinity, let's just have it approach infinity just to look at the most extreme thing that happens here. So if we want to integrate between a and b if we want to find the integral from a to b of this particular function, what we do is what we did in our previous example. We can't integrate between a and b. So what we do is we push the right-hand endpoint or the upper limit of integration for our integral slightly to the left and call it some value t, and then we integrate from from a, let me change that, from a to t, and geometrically for this particular function that would give us the area that I've shaded off of the function, integral function. Then we take the limit as the upper limit squeezes back to b. But the upper limit is going to be approaching b strictly from the left-hand side. Okay? And this is how we evaluate the type 2 improper integral of type 2a. So, well, you can almost guess what type 2b is going to be, where the function is discontinuous. And so we have a discontinuity at the left endpoint. So let's take a look at what happens in that case. So if we have a discontinuity at the left endpoint, and it means we're looking at something like this. So at x equals a, let's say we have an infinite discontinuity, and at x equals b, and all the points actually between a and b, we have a continuous function. The procedure, the process is exactly the same. We can't integrate between a and b. So instead, we satisfy ourselves with integrating between something, a point slightly greater than a, from t to b, and geometrically find that area. So the integral from a to b will equal the integral from t to b of the function, approximately actually, because we pushed the lower limit of integration forward. Then we take the limit as the lower limit of integration pushes its way back to a, so the t will approach a from the right hand side. Okay. The only other part to this, part C, is where we have a discontinuity somewhere between a and b. So we have a discontinuity at, let's say, x equals c, where c is somewhere between a and b. So what that means graphically is this. We have a function, and at some point x equals c, the function has a discontinuity. That c is somewhere between a and b. So b here. Let's say the function does this. And just as the third subcase in the type 1 improper integral was pretty simple, so is this one. So the integral from a to b of the function then is broken up into two integrals, is equal to the integral from a to c of the function plus the integral from c to b of the function. So we've reduced this third case into the sum of the two separate cases, and then we evaluate those as those two separate cases. The first integral becomes a type 2a integral, and the second integral becomes the type 2b integral. Now, I have the same final note about this before we look at an example that I did with the type 1, the third case, subcase, is that if when you evaluate this integral, you find that, say, the first integral diverges. Suppose you found that this first integral diverges, then don't bother to evaluate the second integral. If the second integral is finite or not, or convergent, it doesn't matter. You can't add something that is convergent to something that is, divergent to something that is convergent, and then hope to have convergence. So the bottom line is, if you didn't get what I just said, if one of these two integrals is divergent, then the whole integral is divergent. Okay, and so my word of advice would be, break up, if you're evaluating this type 2c type of integral, break the integral into two integrals this way and evaluate one. Evaluate the first one. If the first one is divergent, then the answer is that the integral diverges. If the first one is convergent, that is, if the first one approaches some number, then we're stuck with having to evaluate the second one. If the second one then also is convergent, then the whole integral is convergent. Add up the two numbers. If the second one diverges, then the integral diverges, regardless of whether the first integral converged or not. Okay, so let's take a look at a couple of examples. So, for example, let me switch back to my other color pen. Okay, example. Evaluate the integral from 0 to 1 of 1 over x squared dx. Okay, so the integral is of the type 2 integral. We have a discontinuity at the left endpoint. So here's, say, a graph of y equals 1 over x squared. So we push the lower limit of integration from 0 to some positive number t, say between 0 and 1. We integrate from t to 1. And then take the limit as t approaches 0 from the only direction it can approach, so from the right. So this is the limit as t approaches 0 from the right. The antiderivative, we've seen this function a few times tonight, or today. Antiderivative 1 over x squared is negative 1 over x. So this is equal to the limit as t approaches 0 from the right. Negative 1, when I substitute the upper limit in, plus 1 over t. Subtracting the antiderivative at the lower limit. And as t approaches 0 through positive numbers, we're looking at sort of symbolically negative 1 plus 1 over a small positive number. 1 over a small positive number is large. So this integral diverges. Integral diverges. I want to note before we look at our next example that this is not a p integral. The p integral is of the form 1 over x to a power, but the limits of integration for the p integral, the one we did in the last hour, has to be between 1 and infinity, and this is between 0 and 1. All right. So I think I only have one more example for you for this lecture. Let's take a look at it. This example is tricky. This example is very tricky. It's not difficult. It's just there's a trick to it. The most common mistake that's made with this example is that students will fail to, or people, anybody evaluating this might fail to recognize this as a type 2 improper integral. The the person evaluating the integral might look at the endpoints of integration and say, oh, the function's defined at both those endpoints, so all we have to do is evaluate the integral as we would do in Calc 1. So I'm going to show you what happens if that's done. So to emphasize, this is a common mistake and this is wrong. To evaluate this is the integral from -2 to 2, and just play along as if it's a Calc 1 integral. This is actually no. This is no. So it would be wrong to write this equals. The integral, the antiderivative is -1 over x from -2 to 2. And if you substitute the lower limit of integration, upper limit of integration, and then substitute the lower limit of integration and subtract, keeping track of all the minus signs. So we subtract the antiderivative at the lower limit, but the antiderivative is already negative, so that amounts to adding, but the lower limit itself is negative. So we get a value here of -1. This is not correct. This is not correct. In fact, can you think of why it's impossible for the integral of 1 over x squared from -2 to 2 to equal -1? It's impossible. The reason is that 1 over x squared is a positive function. If you integrate a positive function between any two limits, if the integral converges, it must be positive. This is the area. This would represent the area underneath 1 over x squared between -2 and 2, and you can't have the area being some negative number. So there's a big red flag that sticks out with this, but a lot of people will just ignore the red flag and state the integral is -1. Anyways, so let's take a look at the correct way to approach this. So the correct way to do this. The correct way to do this is to first recognize that this integral is in fact improper of type 2. The function, let's see, function, just again, 1 over x squared between, oops, give me a second here. Oh, here, it did, okay. The function between -2 and 2 looks like this. Well, the function 1 over x squared looks like this. It's an even function. I'm trying to make it symmetric. Not working out real nice. Okay, so if we're integrating between, let's say, -2 and +2, this is what's going on here. If this limit is to exist, then what this integral represents geometrically is the area underneath this curve. Well, the function is becoming infinite at the origin, so this function has a discontinuity at the origin. So that makes it a type 2c integral. Where the discontinuity occurs somewhere in between the left and right endpoints of integration. Let's evaluate. Let's attempt to evaluate this integral. So the problem then reduces to us splitting up the integral into the integral from from -2 to the point of discontinuity, 0, plus from that same point of discontinuity to the right-hand endpoint of integration. And these two integrals themselves are improper because the function becomes discontinuous at 0. So we concentrate on evaluating one of the two integrals. If that one integral converges, then we evaluate the other one. If the second integral also converges, we add up those values and get the common value of the integral. If one of those two integrals diverges, the integral is divergent. So let's just concentrate on the first half of this integral, the integral from from -2 to 0. Do this homework. Okay. Let's integrate from -2 to 0, 1 over x squared dx. So what that means for us graphically is, let me do this again. That means for us graphically is this. Let's say here's the function, or at least the part of the function that's on the left of the left of the y-axis. We're going to integrate between -2 and 0. We can't integrate to 0, so we push our upper limit of integration slightly to the left. We can't really come far to the left in this case. And we integrate from -2 to that new push to the left upper limit of integration, 1 over x squared dx. And then we take the limit of that as t, the upper limit of integration, pushes back to where it should be in the integral, and that's to 0, but it coming in from the left-hand side. Okay, so let's proceed with this. The integral, again, the same antiderivative as we've seen a few times tonight, more than a few times tonight. So the limit as t approaches 0 from the left, -1 over t. Subtracting the antiderivative gives plus. And keep track of all the minus, but the lower limit is -2. So we're looking at -1 over a small negative number minus 1/2. So this is infinity minus 1/2, which is infinity. So this, the integral that we just evaluated diverges. The integral diverges. So our original integral, the integral from -2 to 2 of 1 over x squared dx, diverges. It doesn't matter what the other half of this computation would yield. It doesn't matter what the value of the integral from 0 to 2 of 1 over x squared is at all. You can't add an infinity to anything. So if the first integral is infinity, it doesn't matter what the second integral is, the entire integral diverges. And that's the end of section 7.8. And I look forward to talking with you again.